we have the system transfer function like this, and the characteristic equation is that. So basically, the eigenvalues of A is order pose Z. Okay, so Z is the eigenvalue of that big matrix A, and this is a characteristic equation of that A. To solve out this is a high order polynomial. So A is equal to 0. The pose are the eigenvalues. So it's kind of high order polynomial. You got Z, very high order. Say you got something here, a coefficient, and you got something here equal to 0. So to sort out all the z's and then test z absolute value less than 1, it's quite difficult to do. So people trying to figure out a way to find all these poles that make sure they are stable without actually solving this polynomial. And this method is called a jury's stability criteria. I'm not sure if you remember, in the continuous time system, we have a Routh criteria. It's very similar to this method. By just looking at its coefficient, A0, A1, up to AN, we can tell if the system is stable or not without even solving any of the poles of the system. So it's a quick check, very easy check. You can manually test this with very high order system. So this is what we're going to do. So we list the coefficient from the equation over there. So just listing the order. Then the second line, we list that in a reverse order. So the first one is from A0 to AN. The second one is back from AN to A0. Then we multiply something, a ratio alpha. We get a ratio alpha multiplied to this second line to make sure the last number, because the ratio is AN over A0. So this A0 multiplied with this ratio, the last number become AM. So all the other values over here will multiply with the same ratio. The purpose of doing that is make sure the last number over here, this last number over here, after this multiplication, they are the same number. Then you can do a subtraction between the first row and the second row. You got this third row. So the third row is 1 minus 2. Because the last row, last item in those two rows are made the same number. So after subtraction, you kind of make this polynomial shorter. You got a shorter kind of series number. So every time you can make it one shorter than the previous. And for this one, you get another ratio between these last two items. So the purpose of that ratio is to multiply this ratio. This number becomes the same as the top one. Then you do the subtraction again. So each time you kind of get these numbers one less and until the very last one. And the rules to check if the system is stable or not is very simple. You just look at A0. All the A's that's at the beginning. If all the A's at the beginning are positive, then the system is stable and all the roots are inside the unit circle. The reason why is kind of a long story. I have to look at the mathematics. So let's just take that for granted. And also, like in the kind of current age, you don't really need something like that. Everything we can do is design a controller. We do that use computer such as MATLAB and other softwares. So those softwares can automatically calculate all these poles and zeros very easily with. So this is a formal statement on how to carry out. Let's look at example because the things here is much easier to be explained if then we use an example. So here is an example. We have A0 equal to 3, A1 equal to 2, and A2 equal to 1. So we write down this A0, A1, A2, first row. Second row, we write down the first row in a reverse order. Then what we do is we figure out what's the alpha. The purpose of alpha is trying to get this last value, A0, to be the same as A2. So obviously here we multiply 1/3 to get the last item the same. So divided by 3, 3 becomes 1, 2 becomes 1, 2 becomes 2/3, 1 becomes 1/3. Then we do the subtraction. So this thing, subtract the first row with the second row. Obviously the last item, this becomes 0. 2 minus 2/3, you get 4/3. 3 minus 1/3 is you got 8/3. Okay, so these two numbers are the new values for our second row. Okay, new values for the second item, third row here. The fourth row is getting from the reverse order of these two numbers. So this 8/3 goes to the over here, 4/3 goes over there. So we just kind of reverse the whole order. If it's longer, you just reverse order. Then we look at the last number. We're trying to make them the same. So this is the last number, and this is the last number. We want to make this equal to that, which we need to multiply by half. Okay, divided by 2. So that's what we are doing, is divided by 2. This one divided by 2, you got 3/4. This one divided by 2, you get 2/3. Then you do the subtraction. Subtraction from the third line with the fourth line. So obviously that's give you 0. That's what we multiply this alpha for. And this one we got 8/3 minus 2/3, which is just 2. Okay, so that's done. When we have only last number, that's finished. Now we check the all the A0s, A1, and A01, 02, all these A's. So this is the first one, check. Second one, we check. Third one, we check. Okay, all of these numbers are positive, means the roots are inside the unit circle and the system is stable. Another usage of this Julie's stability criteria is you can actually not just tell the system is stable or not. You can find a range of parameter. You can find a range of A1 and A2 to make this system stable. So it's just not just only checking one value, actually give you a kind of a suitable range. Say in this case you got 1, A1, A2, that's the first row, second row is reverse, and you do all the calculation. You end up to these are the first number in each one of those section, and we have to make sure these 3 number, they're all positive. Okay, the first one is that's always positive. So you kind of get a range of A2, A1 that suitable for a kind of and stable system. So this also can be used in the controller design to identify what A1, A2 can be, not exact number, but the range. So in here you can see A2 must be absolute value of A2 must be less than 1, and you can get A1.